For 139 years, this object was the kilogram, not 1 kilogram, the kilogram, a small metal cylinder locked under glass near Paris. If it gained the fingerprints worth of dust, the world's definition of mass changed with it. In 2018, scientists threw it out and replaced it with a number and a way to weigh things by counting particles of light. Meet the object it replaced, the international prototype of the kilogram, a cylinder 39 millimeters tall and 39 millimeters wide, 90% platinum and 10% iridium, forged in 1879. It lived at the International Bureau of Weights and Measures, BIPM, in Sèvres, France, sealed under 3 nested glass bell jars. In 1901, the General Conference on Weights and Measures, the CGPM, declared this exact lump to be the kilogram. 6 official copies existed worldwide. The problem: a physical object can drift, collect contamination, or be damaged. A single speck of dust meant a global mass error. This made the kilogram fragile. Over decades, the prototype and its copies slowly diverged in mass by tens of micrograms. Nobody could say which one had truly changed. The kilogram was the last SI-based unit still tied to a man-made artifact. Every other unit, the meter, the second, had already been anchored to constants of nature. The goal: redefine the kilogram through something that never drifts, never ages, and exists identically everywhere in the universe, a fundamental constant. On November 18, 2018, they did it. The fix was to assign the Planck constant, h, an exact value, 6.6260715 times 10 to the minus 34 joule-seconds, frozen forever, by definition. Here's why that defines mass. A joule-second is the same as a kilogram times meter squared per second. Now the meter is already fixed through the speed of light. The second is already fixed through the cesium atom's hyperfine frequency. So once you fix h and the meter and the second are already locked down, the kilogram is pinned in place too. The numerical value was chosen to match the old prototype precisely. So nothing about your weight changed. Your bathroom scale reads exactly the same. Fixing a number is one thing. Making a kilogram from it starts with light. 2 famous equations meet here. Einstein's relation, E equals mc squared, gives the energy locked inside mass. Planck's relation, E equals h times f, gives the energy of a single photon of frequency f. Now set them equal because both describe the same energy. mc squared equals h times f. Solve for the mass by dividing both sides by c squared, and you get m equals h times f divided by c squared. This is the bridge between light and mass. A photon has no rest mass, so in the conventional sense, it weighs nothing. But it carries energy, and energy is equivalent to mass, so each photon has an effective mass, h times f over c squared, that we can use as a counting standard. Let's express 1 kilogram purely in terms of nature's constants. Start from the fixed value of the Planck constant. H equals 6.6260715 times 10 to the minus 34th in units of kilogram meter squared per second. Now rearrange to isolate 1 kilogram. This gives 1 kilogram equals H divided by 6.6260715 times 10 to the minus 34 times 1 over meter squared times second. Next, substitute the official definitions of the meter and the second. The meter is fixed through the speed of light, c equal to 299,792,458 meters per second. The second is fixed through the cesium frequency, delta nu cesium equal to 9,192,631,770 Hz. When the units collapse, the massy power of 10 reorganizes into a clean coefficient. The number works out to 299,792,458 squared. divided by the product of 6.626070015 times 10 to the minus 34 and 9,192,631,770. That equals 1.475514 times 10 to the 40th. So 1 kilogram equals 1.475514 times 10 to the 40th times H times delta nu cesium divided by C squared, mass built from just 3 constants. Now let's count actual photons. Take a single photon at the cesium hyperfine frequency. Delta nu cesium equals 9,192,631,770 Hz. Its effective mass is Planck's constant times that frequency divided by the speed of light squared. Plugging in 6.626 times 10 to the minus 34 times 9.19 times 10 to the 9, all divided by the speed of light squared, which is about 9 times 10 to the 16th. Working that out, the numerator is roughly 6.09 times 10 to the minus 24, and dividing by 8.99 times 10 to the 16th gives 6.777 times 10 to the minus 41 kilograms, so 1 photon carries almost nothing. To build a full kilogram, we divide 1 by that tiny mass. The result is 1.475 times 10 to the 40th photons. That enormous count is exactly the kilogram. 2 warnings. First, this does not mean photons have mass. Their rest mass stays exactly 0. We're borrowing energy equivalence to build a measurement bridge, not claiming light weighs something. Second, fixing a constant isn't arbitrary or circular. The speed of light defines the meter, the cesium atom defines the second, and the Planck constant defines the kilogram. Each rests on unchanging physics, locked together into one self-consistent system. No master object required anywhere on Earth. Sit with that number for a moment. A single cesium photon weighs about 6.8 times 10 to the minus 41 kilograms. To reach a full kilogram, you need its reciprocal, 1 divided by that tiny mass. Carried out precisely, that comes to 1.475514 times 10 to the 40th photons, which rounds to about 1.48 times 10 to the 40th. Written out the long way, that is 14,755,214, followed by 33 more zeros. Stack the photons one at a time, and the cosmic counter has to tick upward across 40 orders of magnitude before the scale finally reads 1 kilogram. Counting 10 to the 40th photon sounds absurd, yet it reveals how science now measures reality. After 2018, every SI base unit is anchored to fundamental constants instead of objects. There's no master kilogram to protect, no cylinder to dust. A lab on Mars or civilization a billion years from now could reconstruct the exact kilogram from the same constants, Hc and the cesium frequency, and get an identical answer. This isn't only theory. Devices called Kibble balances and the photon counting experiments described by physicists like Kettle and Jamieson at MIT realize real kilograms from these numbers today. We traded a vulnerable lump of metal for the permanence of natural law, the quiet end of a long march from human-made artifacts to the constants woven into the universe itself.